Hello, everybody, and welcome to the 53rd episode of the Hyperthesis podcast. I'm Liam.
I'm Patrick.
I'm Pheely.
So today we're going to be talking about superconductivity and some recent news regarding that. But before we get to that, what is our intro topic?
Well, as a preliminary intro topic is the news related to superconductivity. So if you've been paying attention to any science news, or I even saw it just on general news media, there have been claims of a room temperature superconductor that's been created. Now, we'll get into the details of this for the main topic, but I think it would be good to just discuss the current news and the current situation around this, because claims of a room temperature superconductor have been around for quite some time now. I think since maybe even late 90s, early 2000s. People have been like, oh, we invented a room temperature superconductor, and it's always been proven false.
Well, it's not entirely false, but people forgot that it's not just temperature. You find at very, very really strange pressure. So to achieve that in let's say real life, it's really hard. But this one is special because they claim too that they can have it at room temperature and ambient pressure. So it's literally in normal room, which is different.
Right. So typically, superconductors, which again we'll be getting into, only work at very, very cold temperatures. So current modern superconductors, they're known as higher temperature superconductors, but it's still less than negative 100 degrees Celsius. And liquid nitrogen, for example, is commonly used to cool some of these superconductors, which is at about minus 196 degrees Celsius. And liquid helium is used to cool superconductors like those found in MRI machine, which is even colder. And so the idea that we have these room temperature, ambient pressure superconductors is kind of almost a myth in physics that we hear about, one day we'll achieve it. Just one day we will produce sentient AI and things like that. But yeah, this news came across recently with honestly what are very easily obtainable materials, and the research that was pre-printed on a website known as Archive, ARXIV. This is a common preprint area where people can post their papers before they're actually published. But essentially, a paper was posted on there saying, oh, we've been able to use some fairly simple materials to create a superconductor at room temperature and ambient pressure. And mind you, room temperature here is below about 27, 28 degrees Celsius, or under 400 Kelvin. So it wouldn't work in super hot temperatures, but around room temperature. Now, these claims, since the materials were so easily gotten and produced, mind you, the method section of that is interesting to say the least. This is definitely a preprint paper. There are still some errors and some missing information. However, because of the fact that these materials are easy to obtain and the methods are kind of straightforward, a lot of different labs have been trying to reproduce these results. And now this came from kind of not a well-known university. It's not as well established as, say, a place like Harvard or Stanford. However, some physicists from the, I believe the Lawrence Berkeley Institute, is it? They were able to theoretically show that, hey, this is actually possible based on simulations. So there's been a lot of work done, and because it's so easy to obtain these materials and work with them, a lot of work has been done quite quickly. And so now we are seeing a lot of papers being published about this new superconductor called LK99.
Well, I think this is, it's very interesting time, isn't it? Because if it's real, then I think the world will be changed. It's probably one of the most important discovery in recent years. I would say more important neutrino stuff. Particle physicists might disagree, but in terms of impact, like you know, impact to human life right now is if this superconductor becomes a thing, I think it has lead in it, so it might not be the greatest option um, for choice of material, but it would accelerate what we can do with computers and other things, and even for environment.
Yeah, neutrino stuff. I mean, that's kind of cool and useful for physics, but not, yeah, like you said, it's not as useful for the real world. It's not immediately useful to us. Whereas if we can create superconductors, we can create things that don't dissipate energy, which is a huge deal. Like if you think of a power plant, it produces a current, the current goes to your house, and you get electricity. All that current dissipates heat along its way, and you lose a crap load of energy. And superconductors don't do this, and you can use them for a bunch of other things, and it's crazy.
So just to highlight what it's actually made of, so the chemical formula for it is copper, oxygen 25, phosphorus 6, lead 9. And so it's allegedly made through essentially taking lead apatite, not apatite like you want to eat, but apatite, which is actually used for fertilizers. So it's this lead apatite compound, and adding a small amount of copper in a certain way to it allows it to become superconducting. And this has actually been around for quite a while. It was started to be studied around 1999, hence the name LK99. And the LK comes from the names Lee Kim, who were the two people working on it. So this research in 1999 was actually replicated in a lab in 2023. So it hasn't been validated yet, but it's older research, new in terms of physics, but old in terms of, well, research that's actually coming to light again. And just as an example, if you're, say, listening to this on a computer, or you have a computer, you might be able to hear the fan spin. And that's because a lot of heat is generated by the components of your computer. Now, if we were able to fit a superconductor in there, which didn't lose energy in the form of heat as it ran, then we would have much more powerful computers, because we wouldn't be limited, for example, by the thermal output of computers. So you can have a lot more going on without having to worry about heat, because that's kind of one of the issues with, for example, CPUs, is the heat they produce, or GPUs especially. And so if we have superconductors, we can eliminate the amount of cooling that we have, and then we can have more efficient machines at the very least. And again, this is applicable in many, many different areas. And as a former particle physicist, I would say that this is more important than neutrinos. Don't poach me for that.
Well, I think that's a good transition to our main topic, which is the same thing, which is we're gonna give some idea. We mentioned before about superconductivity and stuff, but we never really get into it. I think Liam would know more on the quantum side of things, because I think it's pretty close to BEC stuff, right? I mean, the temperature wise, so the effect. So for our main topic today, we're gonna be discuss a little bit about superconductivity, and it's when you put super in front of things, some people will be like, well, this is something very special, or just call it super. Maybe if we are Russian, we say super a lot, but who knows? Anyways, for superconductivity that we're going to be discuss today, superconductivity is actually a property of certain materials that normally if you're a conductor, you can basically carry electric charge and the current and make them go through the lines, the wire or whatnot. And if an insulator, it really hates charge being moved. So even though a conductor have charge move in a certain way, it has some, if you think of classical way, it's like have friction, right? When you want to roll a ball down the hill, or like push a car, there's a friction, or push a ball, push a block of wood across the floor, there's friction. And that friction generates heat. That's how you lose energy. And if in a classical term, if you want to have some kind of super conductivity, so basically if you're on like frictionless surface, imagine you're on ice. Well, it's not totally frictionless, but have much less friction than normal. So things just glide, right? It wouldn't stop. Like in space, you shoot a rocket out and or like shoot out a ball into space and it just won't stop because there's very, very little friction. And for superconductivity, it's the same thing, but with charge. So when you push a charge through a wire, usually it would lose energy because there's something like equivalent to friction. Maybe there's some disturbance in magnetic field or electric field, property material itself. You have to go through, the entire atoms and molecules. But there's an interesting property of material when for some metal or alloys, when you cool it cold enough, that friction just goes away. So the current can just flow through it smoothly and without losing energy. It's similar to superfluids, really. Well, I mean, the concept is similar, right? If you are superfluid with, I think Denise touched on a little bit in couple episodes ago, where you wouldn't have friction in fluids, so fluids can just flow through anything through the volume without friction. So when you put a lot of the word super here, it usually means there's something missing, mainly friction. And the temperature at which they become superconductor is called the critical temperature. And once you pass that critical temperature, which you can calculate, and things will be superconducting. So, and the transition into superconducting is actually quite unique because it will expel magnetic field when it goes to this superconducting state, and you can test it if it's superconductor or not by trying to find what we call the Meissner effect. If you see some videos or pictures of some of you may have done in the lab yourself, when you can cool it down to superconducting temperature, some piece of metal, and you put it over a magnet, and it's actually floating, and you can spin it around and stuff. So that's one of the things that indicates superconductivity. So, gotta touch on a little bit more on the Meissner effect too. So the Meissner effect actually was discovered by German physicist Meissner, of course, W. Meissner and Oschenfeld in 1933. It's a while ago. So it's basically the expulsion of the magnetic field from the inside or in the interior of material. So when they start to become superconductor, so basically losing the resistance. Well, it's like friction we call it resistance. So it starts to lose its resistance to the flow of electrical currents when it starts to become below the critical temperature or the transition temperature. It's usually pretty close to absolute zero. That's why, as Patrick mentioned before, it usually you need like liquid helium to cool it down. And that is actually one of the big challenge to create superconductors, because usually you need very, very cold. Think of 4 Kelvin, which is like 269 degrees Celsius below zero. Like it's this very, very cold. So to do that is sometimes takes so much energy to cool it down to that level to achieve this superconductivity. So in this transition temperature, usually around 1 Kelvin to 10 Kelvin, so really close to absolute zero, and like or some material even closer. I think tungsten is like 0.015 Kelvin. It's really close to absolute zero. And also it's really sensitive to this magnetic impurities. If your material have impurities, the transition temperature would also change too. So even a few parts per million of manganese in zinc lower the transition temperature considerably. So sometimes you want the material to be as pure as possible, or the alloy to be as pure as possible, because the superconductivity, the critical temperature, is difficult to achieve.
Oh, so I just think at this point it's important to talk about the mechanisms behind superconductivity, because we know how we can test for it using the Meissner effect, and we know that there's a transition temperature somewhere for different materials, and it is different for each different material, whether it's pure zinc or whether it's these more advanced superconductors like the ones that we were discussing in the intro topic. But essentially, there are two different types of superconductors that we have. The first, which are conventional, and then the second of which are unconventional, of course. So these conventional superconductors, they are the very low temperature ones. So these are the ones that were first discovered and, say, need liquid helium or other very, very cold cryogenic material to keep cool. And they tend to be the most basic ones. For example, zinc, which is able to superconduct at a certain temperature. Now, for conventional superconductors, these use what are known as the Bardeen-Cooper-Schrieffer theory behind superconductivity. And essentially what this says, and someone jump in if I haven't explained it fully, but essentially is that you have a pair of charged particles that are moving through the superconductor. And what happens is that once the superconductor reaches this critical temperature or goes below it, the elements of that superconductor are arranged in such a way that when you have, say, an electron moving through it, it essentially creates this kind of positively charged hole as it moves through the superconductor. And this positively charged hole is able to attract another electron. And so these two electrons are able to move together, one creating this positively charged hole as it moves through, and then the other one following with essentially no resistance. And so this Bardeen-Cooper-Schrieffer theory names these electrons as BCS pairs. They were at one point known as Cooper pairs, but now we know them as BCS pairs, and essentially they're able to move through without resistance.
A lot of people still call them Cooper pairs as well. And I've been silent this whole time because I've been scavenging Wikipedia. And yeah, like I knew what you said earlier, Pheely, how there's a connection between Bose-Einstein condensates and superfluids. There's a connection between them and superconductivity. And I knew that because the Russian physicist Bogolyubov is famous for something he came up with called the Bogolyubov transformation, which is how he partially derived this BCS theory and the fact that the Cooper pairs can give you superconductivity. But also in Bose-Einstein condensation, that's how you derive it. You do all this Bogolyubov transformation stuff, and that's actually also what Stephen Hawking used to derive the Hawking effect. So it turns out that superconductivity and this Bose-Einstein condensation, which I always talk about, but I'm not going to talk about much today, they're very, very much related. They break symmetries. The math describing in them is very similar. They relate to phase transitions, so it's all really interesting stuff.
Well, I think one thing that Patrick mentioned about mechanism, I think is how I visualize it too for superconductor, because material at high temperature or any temperature really, well, that's not absolute zero, has some disorder in it, right? Like sometimes material just orient itself certain ways in terms of molecules and structures, and in terms of energy, there's not much gap, especially insulators for electrons to go through. That's why they resist it. But there's a theory was that, well, once you get low enough temperature, that disorder kind of goes away quite a bit, and this is a gap in energy level that electrons are allowed to access. And like you said, if one electron just go through, it basically pulls all the electrons through without any friction, because there is that gap. in the energy levels that allow electrons to freely pass through. But that gap would be closed if there's so much disorder or all the energy is around, right? That's kind of muddle up that path, even though it's still conducting. But if you imagine you have to walk through mud, you're gonna lose energy more than, let's say, if it's cold enough, the snow plow comes in and then you're golden.
So since you did mention BECs, there is also some phonon related stuff with BCS theory that interacts with the electrons as well. But that's mainly conventional superconductors. Essentially, the electrons like to pair up together and don't really cause resistance. Because in a normal wire, the resistance comes from the electrons essentially bouncing off the atoms within, say, a copper wire. And so you have this net movement of electrons, but they're bouncing off so much that there's a lot of kinetic energy being transferred, and then there's also a lot of inefficiencies with that. And that's where a lot of the heat comes from, is these inefficiencies. So these inefficiencies are removed in conventional superconductors through Cooper pairs.
And this connection between Bose-Einstein condensation and it's these Cooper pairs. It's the fact that it's weird. Two electrons would normally repel each other, and you guys have already said this, but one leaves a hole, so one of the electrons follows the other one as it moves around. And these are two fermions. An electron's a fermion. It has spin 1/2. So when you have two of them together, you get this kind of quasi-particle. You get something with spin 0 or spin 1. So you get a boson, and that's why the math that describes Bose-Einstein condensation is, I don't want to say the same, but it's very closely related to the math that describes superconductivities, because these Cooper pairs are bosons and they can now occupy the same quantum states, which is something fermions can't do. I don't know, my research is always about universality and how all these different things in the universe seem to be described by the same math, and this is one of those really good examples. It looks like a phase transition, just like Bose-Einstein condensation. Something gets really cold and then suddenly it behaves differently past some critical temperature. The math looks the same. It's really cool.
Unfortunately, however, the math does not look the same for unconventional superconductors. And unconventional superconductors are classified as high temperature superconductors. Now, this isn't high temperature from normal everyday life, but it's warmer than 4 degrees Kelvin and is more so maybe around 100 degrees Kelvin, if not a bit higher even.
Yeah, so the three of us actually, we had a solid state physics class that we took, and it had a lab component. And we actually got to see a high temperature superconductor in action. And by high temperature, we mean whatever temperature liquid nitrogen is at. I don't know if you guys remember that, where we made one of these. We used this Meissner effect. So if you have this superconducting metal, you get it around the temperature of liquid nitrogen, which I think is like 70-ish Kelvin.
Yeah.
Something like that, maybe.
A little
Maybe
bit
it was
higher.
90.
93.
93, okay, yeah. And then it levitates because the magnetic fields get expelled from it. They don't simply pass through this little brick of superconducting metal. They kind of like warp around it, and that causes it to float and hover there. And it's really cool, and it's really cold. And I remember when we did that lab, I accidentally broke the magnet. So our lab instructor was not happy with me because it was I don't know how expensive it was, but it was expensive enough magnet that they were not pleased with me.
Although, so the superconductor we used in that lab was a yttrium barium copper oxide superconductor, or YBCO, which was actually the first superconductor that was found to have a critical temperature above that of liquid nitrogen. So, sorry, I mixed up a little bit, but liquid nitrogen is 77 Kelvin, and at about 93 Kelvin is where this critical temperature is for the YBCO. So we had like a little disk of that. And another cool thing with these yttrium-based superconductors is that if you make them thin enough, the Meissner effect, there's an additional effect to that. So we can test with the Meissner effect, see that a magnet levitated, in this case, above the superconductor. But if you have a thin enough sample, you can actually levitate the superconductor over a magnet and actually lock its position. So not only is it essentially levitating over it, you can actually lock its angle. So it has, I think, 3-axis freedom in where it can be, or maybe 2-axis freedom in its positioning, which is super cool and only works if they're really thin, because then the magnetic field lines can pass through it and kind of lock it in place.
Yeah, but back to this whole high temperature superconductor stuff is that you have to be, as a physicist, when you hear high temperature superconductivity, you're like, wow, negative 180 degrees Celsius. Like, that's so high for a superconductor. Which is why this recent news where they propose like an actual room temperature superconductor is such a big deal, because we can create superconductors, but they're really, really cold. And even the ones we call high temperature superconductors. So if you can create one at room temperature, well, that's some Nobel Prize material right there. You can save the world a lot of energy. You create these really good computers and all kinds of stuff that I probably am just unaware of.
But going back to the mechanism for these high temperature superconductors, which may very well also be the mechanism controlling this new possible room temperature superconductor. So these are unconventional superconductors, and we don't actually know exactly how they work. So with conventional superconductors, we have our BCS theory, which forms the Cooper pairs. However, there is still active research going into how these high temperature superconductors work. We wouldn't get into it too much, but there's a weak coupling theory in which there is some sort of weak symmetry in a high temperature superconductor between the electrons. And yeah, there's a lot to do with spin fluctuation and different order parameters for high temperature superconductors. Again, we won't get into it, but essentially, there's the weak coupling theory for the electrons moving through these superconductors, which aren't just simple crystal lattice structures, but are a bit more complicated. And then there's also an interlayer coupling model, which is kind of based on BCS type symmetry in a superconductor, but enhances superconductivity itself. But there's a whole lot of research that's active going on in this. The last paper that I saw for this was in September 2022, which talked about a new process for the electrons to move through the material, but that is still a very hot topic for research. So if you want to do research into it, there's a lot going on for high temperature superconductors, and it looks like they use nuclear magnetic resonance, which also uses superconductors in of itself to actually probe the magnetic field around the atoms involved in the superconductor to see what their arrangement is like and how the electrons might be moving. So very advanced research going into it.
Well, I want to touch a bit on the applications of superconductivity, because we mentioned it quite a bit actually, but I want to get into it. So I think the most prominent use is in the medical field, which is the MRI, or some people know it as in a better name, NMR. But people are scared because it used to be called NMR, nuclear magnetic resonance, and the sentiment of people when they hear nuclear, that's not good. So they basically shift one, take it, and now just MR. Well, need one more letter just for good luck, and MRI, magnetic resonance imaging. So what's the thing about MRI is that it requires a very large magnetic field. So basically, they want to flip spins in your body, and once you flip it back or turn it off and put it on the other side, different elements would give out different signal, basically, or different reaction signal. So you can tell, if there's water here, if there's something that's not water there, or you can have this imaging coming up in basically as many in the 3 dimensions, really depend on how you slice it. So, but the challenge is to create very strong magnetic field. And if you remember from first year physics, we have something called Biot-Savart law, which basically I think is some kind of integral of mu naught over 4 pi something dl cross r over r cube or something like that. Anyway, so it depends on length of the wire, the current through the wire. And so you want as high as current as possible. If you look at the MRI machine, there are big donuts. So they basically put a lot of wire into a cylinder or a circle, and just run the current through it really fast. Oh, not fast, but a lot of current through it. But now you could imagine if you run a lot of current through a wire, there's something called resistance. And resistance like friction, and those friction generate heat. And the more you generate heat, the more resisting your wire would be. So it's actually worse, right? You actually like hot wire and electrical wire on a hot day has higher resistance. It's just a property of material. So you want to have as cool as possible. That's why also like you want your computer to be as cool as possible. And what happened is that if you try to put that much current through, it's gonna burn everything. So the solution they comes up with after this discovery of superconductivity is to use superconductors. So why do MRI machines cost so much to run or to maintain? Because they have to order these liquid heliums, which are very hard to find and quite expensive and filled in all the time. I think it's actually cheaper to keep it running rather than shut it off and try to start it back up again. So these hospitals or research centers have to keep a constant supply of liquid helium, which if you know, heliums are light gas. Once it's left the ground, it would just keep floating because it's lighter than anything else and leave into space. So it's one of the gas that's really hard to find, and so it's quite expensive. But so once we have those big ring of metal cooled down to superconducting temperature, then you can put as much current as you want without generating heat. So you can generate this really large magnetic field that can be used for medical purposes and other stuff.
I think those machines probably have like good closed systems to keep the helium from kind of evaporating as much as possible, and that's why keeping them running is probably easier. So I'm not sure. Maybe Patrick knows more about that.
They have excellent systems for keeping the helium in. So pretty much they need to be refilled very, very seldom, like once every few years, just because of the fact that they recycle the helium that they use. And it's a very complicated process with the plumbing involved. But yeah, essentially once the helium is in there, it's in there for quite a long time. And there's so much insulation involved in everything that they don't really need to like constantly replace the helium with cold helium. It does a very decent job at staying cold. Now, of course, it's 4 Kelvin, so it still has to be kept quite cold and it's very energy intensive. But yeah, you wouldn't see like helium leaks with an MRI machine. And it's if you look up videos of a helium dump that's done by an MRI machine, this pretty much breaks the machine, but essentially exhausts all this helium at once. And almost every hospital or place with an MRI will have these helium dump vents where if you press the button, it will vent all the helium at once. The superconducting no longer works, so that's what breaks the machine. And then you just see this massive plume of water vapor from the helium, which looks really cool, but it's detrimental to the operation of the machine.
And also, once it's run and you keep that superconducting temperature, you put whatever currents in, it's gonna stay there and loop theoretically or impractically forever. But even it's still superconducting, but I don't think it's totally frictionless or resistanceless, because I think the shape of the wire, if we believe that electrons lose energy from colliding, but if you're moving around in circles, there must be some kind of force acting on it, right? Listen, centripetal force, basically. So it might be very negligible, but in principle, it shouldn't be able to run forever. But in terms of years, maybe. You just you don't need to really add more current or magnetic field in there. But you still want to control the strength of magnetic field. I think that comes in where you need to control the current. But I have never worked with any real superconductors in professional capacity, so I don't know how if they need to really change current that much, is it important to change the current. But on the other than the MRI, we also can have those maglev magnetic levitation railways and stuff, because magnetic field are not that strong in terms of it falls off quite harsh. It's like auto forces, really. But you think about it, you pick up a permanent magnet, your fridge magnet, right? It's quite strong when you put it really close together, but you push it away a little bit and then it's gone. So what it's gonna try to do with the maglev is basically magnetic levitation, to use the magnetic field with put really high current in a magnet to lift the train up from the track just a tiny bit, so it doesn't have friction against the track, and that would save a lot and lots of energy, or if wear and tear would go down too. And sometimes you don't even need to lift it all the way up. I mean, it helps to reduce the weight too. So, and this type of superconductors could be, or even room temperature superconductor, helpful. So now you can put a lot and lots of current through the train tracks to lift these trains up. And other ones would be, let's say, power grids, for example. We lose a lot of energy just transferring through the country, right? It's not just about energy we generate. Well, let's say we generate 100 watts or 100 joules, right? Or 100 unit less, like natural unit we love. So 100 units of energy. Well, maybe you can store 40% of it. Maybe you can store 40 of it. Well, but if you send out for people to use, maybe you can use 80% of that. That's really high, right? But if you send it further and further, maybe the receiving end would get only 30% of it. But however, if we somehow have superconductors as power grid, we should not lose more than 1%, let's say, if things go right, or we might not lose at all. Imagine the power we use right now, and we can basically double it, right? Just from changing the material, and that should be very revolutionary just for the environmental standpoint and energy standpoint.
Another thing aside from power transmission is power production. So everything except solar panels that I can think of off the top of my head uses turbines or these electric generators, which are also electric motors, which are essentially permanent magnets moving past copper or wire coils. And this movement is what creates the electricity. And so if you have superconducting generators, then there goes any wasted heat. So you can actually get even more. And I believe they're testing this type of technology with wind turbines right now.
Yeah, I think it's almost all the electricity generators are dynamos, which is the inverse of the motor. So that's why I like to, like when you say there's motor in the car, like it's like no, it's an engine. Oh, because they're different. Motors use, in a technical term, use electricity. You run electricity through wire. There's some magnets, and it make that magnet spin. But the opposite is also true. When you spin something, spin the magnet, it also generate that current back. I think it's one of the electric car braking system use that braking to generate the current back into the car too. It's very similar things, but almost all electricity generators, think of turbine, windmills, well, those stuff, there's something spinning. And that spinning, when you would put magnets inside it, it generates this alternating current That's why I think, well, it's better to use direct current, but easier to generate alternating current. I think that's why it won, right? Like, it's why it's everywhere, because it's so much easier to generate, to, well, not to really store, but to propagate.
Uh, Going to a completely different use case in they're used in some types of particle physics, but there are these devices known as superconducting quantum interference devices, or SQUIDs. And these SQUIDs are essentially extremely sensitive magnetometers. So they're able to record very sensitive or very, very small changes in magnetic field, say as an object is passing through it. Now, these SQUIDs are used in a couple different applications, but one such application is, or was, with the METAL project, which was aimed at finding monopoles or magnetic monopoles, something which we have not discovered. We have electric monopoles, we have positive and negative charges, but we've never witnessed or discovered a magnetic monopole. And so what the METAL and now the MAP collaboration, I think is the newer version of it, what they're doing is they're looking for monopoles that are produced by the Large Hadron Collider. And what they do is they have these very long solid tubes. I forget the exact material that they're made out of. But essentially, if you have a monopole, what you can do is you can take these very long tubes that are placed close to the Large Hadron Collider and run them through a squid, which again is superconducting, and they can look for changes in the magnetic field. And if they see, say, a positive magnetic field that is not counteracted by a negative magnetic field of a dipole magnet passing through, then you have proof of a monopole. And so that's more of a sciencey use for these superconductors, but they could be everywhere, especially if we get these room temperature ones.
Well, the existence of monopole in itself is quite controversy, isn't it? Because, like, in undergrad, I think when we first did E&M and we do like multiple expansion, there's some proof that said, well, some of these poles are not theoretically possible. So I'm not sure if maybe the theory was lacking, or maybe sometimes they get broken all the times, right? Like those symmetry got broken all the time in particle physics. It's ridiculous how much is broken. Nothing is 100%. So I'm not sure about the existence monopole, because that would be very revolutionary if you find some, because we know we have positive charge and negative charge, we can do things with it that are different, they're opposite, but we never find any magnetic thing that's on itself, like north or south, right? And that really breaks down this understanding we have for thousands of years of magnets.
Yeah, I think Maxwell's equations, they just tell you can't have magnetic monopoles, but there's still a lot of people looking into them. And additionally, electromagnetism is not the complete theory of everything, right? Like, I don't know what the better theory of quantum electrodynamics tells you about monopoles. I've never looked into it. But it's one of these things where maybe our theory is wrong and it needs modification. Maybe it's fine. But as far as we can tell, we haven't found any magnetic monopoles yet. So maybe superconductors can help confirm or deny that.
And I will say that's another use for superconductors is for experiments like the Large Hadron Collider. They need superconductors to actually essentially bend and also accelerate the particles that are going around and around. So they use quite a lot of cryogenic material. And so if we had superconductors, then we might be able to build larger accelerators for cheaper. So again, so many use cases, so many applications. Pretty much wherever there's electricity flowing, superconductors would be amazing.
Well, maybe we should build one in space. Space is very cold, and it sucks all the temperature or all the heat away from you, right? So it might be a good place to build it.
Although the thing about that is that unless you really the only way to remove heat in space is through radiation. So you have your convection, you have your radiation, and you have your there is a third way that you can remove heat, and in space you only really have radiation, so you need quite a lot conduction.
Conduction,
is the other
convection,
one.
and radiation.
Yeah. And so in space, you only have your radiation. So you need like very large radiators to be able to move the heat that's produced in a lot of these experiments that would use superconductors.
Yeah, that makes sense. Because even though space is really cold, there's not that much, like transfer of heat, right? It's really difficult. So I wonder maybe conducted in some planets that's far away from the sun that's naturally cold, right? That might be more what's it called, practical.
Yeah, do it on like Europa
Pluto.
or something
Oh,
like
it's
that.
not a planet.
Well, it's a moon. It's fine.
Yeah. Is it a moon? Or is it like a part of the that asteroid belt around the solar system?
No, Europa's a moon.
No, I
around...
think of Pluto.
Yes. Well, Pluto. Yeah. Let's not get into that. That's for another conversation.
Anyways, I think to wrap this up a little bit on superconductivity is that let's see what happens with the news here that if they actually found the room temperature and ambient pressure. That's very important asterisk that you have ambient pressure, that basically room temperature. The STM, I think, what is it called? Standard, I don't know, atmospheric STP, yeah, STP, at the standard pressure and temperature. So that's to be exciting to see if that happens. The world would change for sure. But in terms of normal superconductivity, we know quite a bit about it, but there's still a lot more to discover and to invent, I think, even though applications, the way, maybe the new way to maintain the cryostats. Maybe, you can build better computers with it. So you guys have any final remarks before we move on to the story?
Just one final thing is that even if this does prove to be a superconducting material at room temperature, this LK99, and standard atmospheric pressure, I'd be curious to see what it would cost to produce. Because another type of material that we've heard about for a long time as a super material is graphene. And graphene, it was supposed to be this wonder material. It could possibly even be superconducting. It was going to be in all the circuits. We were going to have clothing made of graphene, cars made of graphene. Everything was going to be made of graphene. Where is it? It's still in the lab because it's so hard to mass produce. And given that that's made of carbon and it's just essentially a sheet of carbon, that's very easy to produce, whereas this is kind of a lead apatite infused with copper. And some of the current research is saying that, getting that infusion of copper or the doping of copper just right might be the trickiest part. We can talk all we want about having superconductors everywhere, but if it's not easy to mass produce, then it will stay in the lab or in very niche applications like an MRI.
Well, let's see what happens. Because maybe the engineers will figure it out, but who knows?
Yeah, there's definitely going to be a lot more applications for it than we can predict right now, if it turns out to be one. But anyway, thank you very much for that, guys. And now we need to get to our story. But of course, Patrick needs to tell you about how to reach us and lie to you about memes that I never post.
Well, I mean, I figure if I say it enough, then we will get more memes because for those of you that don't know, Liam is our meme lord, or he was at one point during our undergraduate, where he had an entire wall at his desk filled with memes. So if you want to see those memes, you can find us on Instagram. We are at the Hyperthesis, where you can send us a DM if you have any questions or suggestions for topics, or if you are a professional in your field, whether you use superconductors or not, we would love to have you on. Doesn't matter the topic, just has to be sciencey. Whether you study bats or Bose-Einstein condensates, we would love to have you on. You can also reach out to us at our Gmail. We are hyperthesispodcast@gmail.com. You can send us an email. We're pretty good to check up on that. Other ways you can contact us include YouTube. So we are now caught up with all our YouTube videos, which is fantastic. So thank you to Pheely for that. We are silently giving him a round of applause in the back. But
A trooper.
all our YouTube videos are up to date, and we will be making an effort to keep them up to date as we post episodes. So go check us out on YouTube, subscribe, like, share, leave some comments. I think we might have that enabled, not quite sure. But yeah, that's another way to reach us. So we have our email, we have YouTube, we have our Instagram account. Now, if you are listening to us, which I assume you are, if you're hearing us, you probably found us on some sort of podcasting service. We are based in Spotify. However, we are found pretty much in whatever podcasting service exists, whether it be Google Podcast, Apple Podcast, Audible. You can find us anywhere. So if you can, feel free to leave us a review or suggestions of topics you would like to hear. We are more than happy to get suggestions, and we get very excited when we get DMs with suggestions. So reach out to us, give us a listen, and share us, rate us, subscribe us, like us, do whatever you need to do. And especially if you want to see some fun memes from Liam, really send us a message. Let us know that you love them.
I'll work on some more. I posted one the other day, I think, although I don't remember now. So at least I'm trying.
That's all we can ask for. So, to wrap up today's episode, I will be finishing with a quick story, and that's about 3 physicists who were involved with superconductors. So, we talked during our main discussion about BCS theory, which is named after Bardeen, Cooper, Schrieffer, who were all American physicists who all worked on superconductivity. And their work has been fundamental in understanding both how superconductors, at least the conventional type work, as well as some stuff related to Bose-Einstein condensates, which is what Liam talked about for a little bit. So I just want to delve into their lives just a little bit, just to explain who they are and where they come from. So we will start with John Bardeen. So John Bardeen is an American physicist. He was born in Madison, Wisconsin in 1908, which is a city and state in America. And he actually won the Nobel Prize twice. He is the only person to have won the Physics Nobel Prize 2 times. Now, we've actually mentioned him before when we were talking about transistors, because he shared the Nobel Prize with William Shockley and Walter Brattain for the invention of the transistor. So this man was already heavily involved with electricity and how we can use different materials to do different things. So he actually won the Nobel Prize for that in 1956. And of course, the transistor was revolutionary. It started the information age, and we find it everywhere now in cell phones and computers, and even I think like temperature sensors and whatnot have transistors. So pretty cool guy already. He did receive his PhD from Princeton, and he was involved with serving in World War II, and he was a researcher at Bell Labs. You'll find that there's a very common pattern among especially material physicists and people like Bardeen, and that they got their start in places like Bell Labs, which was renowned for very like cutting edge inventions like the transistor. However, he also began to work on superconductivity and received the Nobel Prize for that with the 2 other people in the name BCS, Cooper and Schrieffer, in 1972. So just phenomenal to win the Nobel Prize once, to win it twice for 2 different revolutionary ideas is incredible. And so his second Nobel Prize was for specifically figuring out the superconductivity of conventional superconductors. And he actually appeared in Life magazine's 100 most influential Americans. So really influential. Quite an amazing guy who studied mathematics and physics and really revolutionized modern electronics. Now, The second person involved in the BCS is Leon Cooper. So a bit less is known about Leon Cooper. He was didn't win 2 Nobel Prizes, but he still is a Nobel laureate for the BCS theory of superconductivity. And he was born in February 1930 in the Bronx, New York City. Now, he studied both at the he studied at Columbia University, receiving his PhD in 1954. And then he spent a year at the Institute for Advanced Study, and he taught both at the University of Illinois and Ohio State University before going to Brown University in 1958. For those of you that don't know, Brown University is quite a renowned university in the United States. He has had many different accolades and membership and honors in his name. However, in physics, one of the best things he's known for are Cooper pairs, which is, again, that pairing of electrons working with phonons to be superconductive in these conventional superconductors. And actually, Leon Cooper is part of the inspiration for Sheldon Cooper, the character from the Big Bang Theory. So again, another very substantially influential physicist, and he's still alive at the age of 93. So good on you, Dr. Cooper. The final member of the BCS crew, not to be confused with the BTS crew, is John Robert Schrieffer. So Schrieffer was also an American who was born in Oak Park, Illinois, and was again one of the 3 recipients of the 1972 Nobel Prize. So he started at MIT, where he first started in electrical engineering before switching to physics in his 3rd year. There he completed his thesis focused on heavy atoms under the direction of John C. Slater, who I believe we've also mentioned before, in 1953. From there, he continued his work on material physics and electronics, and it's in his 3rd year of his graduate studies, he joined Bardeen and Cooper in developing the theory of superconductivity. So he was also quite young as well. He's a year younger than Cooper, and so they were working on this idea. And in 1957, he was actually in New York City on the subway when he thought of how these electrons could move in pairs. And of course, Cooper pairs are what we discussed. However, Schrieffer was able to do the mathematics behind that and was able to introduce the behavior of these Cooper pairs. So he was able to share his equations to the rest of the group, and they were able to actually work out this idea of superconductivity. So goes to show you that public transportation is great for thinking, if anything else. So from there, he spent some time at the University of Birmingham, however, mainly remained within America. And he died very recently, only about 4 years ago, at the age of 88 in Florida. So that's a little look into the lives of the people responsible for revolutionizing the theory behind superconductivity and really taking a look from the quantum aspect of material physics and figuring this out, and they were well rewarded for it for the 1972 Nobel Prize. So very interesting people, and their legacy continues to live on, whether with TV characters or with their theories, but just astounding people, and the fact that the 3 of them were together was just excellent.
Thank you very much for that, Patrick, and thank you as well, Pheely, for meeting today and having this good recording. So I guess only time can tell if these room temperature superconductors are legit or not. And I guess if they end up being legit, you'll hear from us. So thanks for joining us, and we'll see you next time.
Take care.
Bye, everyone.
Peace out, yo.